OS dev is hard. It's been over a year since I started doing OS dev by myself without getting a single dime out of it. But I can say that this journey has been incredibly interesting, and honestly it's just the beginning. Because I remember back in college I was doing research with this guy, and he told me it took him almost 10 years to build something truly remarkable in operating systems. At first I didn't believe, but I checked it and dude, this guy was 10 years trying to reach the state of the art, to do something academically remarkable, and he did it. It was amazing, but it took time. So the first thing I learned was that patience in this area, OS dev, patience is key. So OS dev taught me more than just technical skills. It taught me how to be patient, because you don't understand things on the first or the second read. Sometimes you have to read the same thing like 5 times, and that's okay, because memorizing doesn't work here. You have to understand, and true understanding takes time. One of my biggest struggles was consistency, because I would start something then drop it for a week, and when I came back it was like starting from scratch. OS Dev helped me a lot to realize that to keep up I needed consistency and practice. That's one of the reasons I'm starting this video series. It's not just to share what I learned, it's also to help me remember and solidify what I have researched in the past. So my goal here is to make this series as clear and as helpful as possible, especially in the early episodes, where we'll be writing a bootloader, the small piece of software responsible for booting an OS on a computer. This won't be easy, it'll take time. I'll need to study a lot to explain concepts I don't fully understand now. But I believe it's going to be a worthwhile journey, so if that resonates with you, please leave a like, and don't forget to subscribe. Thanks for being here, and let's get to the video. In this first chapter, we're going to be looking into the boot process, step by step, to understand what happens from the moment we press the power button until our kernel takes over. Keep in mind that some concepts introduced here will be covered briefly, and we'll dive deeper into them in future videos dedicated to each phase. Whenever you push your power button, the first thing that happens is the post routine, which is power on self-test. Post is run by the BIOS, which stands for Basic Input-Output System. BIOS is a low-level firmware stored on your motherboard, and it acts like the bridge between your hardware and any software that might eventually run, including the operating system. The first thing the BIOS does is run the post diagnosis to check if your essential components, for example RAM, CPU, keyboard, and basic I/O devices are all working. And if something fails, BIOS might output a series of beep codes or display an error. For example, if everything is correct, in modern computers the usual response is to have a single beep. More than one beep means errors that need to be handled. But if everything checks out, post finishes and it's flushed away from memory. And after that, BIOS continues the boot process by looking for a bootable device. After post completes, the BIOS starts scanning for a bootable device. And this could be a hard disk, USB stick, CD-ROM, or even a floppy. But how does it decide if a device is bootable or not? Well, it looks for a special place, the so-called Master Boot Record, or MBR, which lives in the very first sector of the storage device, sector 0. The BIOS will be looking whether the sector ends with a so-called boot signature or magic number, which is 2 bytes, hexadecimal 55, and AA. These values must appear exactly at byte positions 510 and 511. Considering the sector has a size of 512 bytes, this means that they're in the last position of the first sector. If they're not there, BIOS assumes the device isn't bootable and moves on to check for the next device. If the signature is present, however, BIOS loads the MBR into memory at address OX7C00, and that's where execution begins. This is the exact point where our custom bootloader will live. Once the BIOS loads the boot sector into memory, it then passes control to the bootloader that was loaded in that sector. Then it jumps to Rio Mode, the initial operating mode of the CPU. Rio Mode is a 16-bit mode that was designed to be compatible with the original Intel 8086 processors. That means that we can only access 1 megabyte of memory, and we don't have protection features or multitasking. It's like programming in the early 80s. Memory in the Rio Mode is accessed using segment offset pairs. This gives us a way to address memory beyond 64 kilobytes using 16-bit registers, but it's tricky and it has lots of limits. The important thing to know is, this is the mode our bootloader will start running on. So we'll have to do everything here, like printing text, setting up the GDT, and eventually switching to protected mode, using just 16-bit instructions. That's why understanding Rio Mode is so important. It's the foundation for the rest of the boot process. So after we're done with Rio Mode, we can finally switch to protected mode, and that's where things get interesting, because in protected mode, we get 32-bit registers, 32-bit instructions, and a nice flat memory model. That means that we can work with up to 4 gigabytes of memory without dealing with all that segment offset madness. And as the name suggests, it also brings memory protection. Stuff like isolating memory between processes, setting up privilege levels, and making sure that code doesn't accidentally mess with something that it shouldn't. So to actually switch to protected mode, we need to set up something called Global Descriptor Table, or GDT. This is done in Rio Mode, by the way. GDT is basically a structure that tells the CPU how to interpret its segments. So where they start, how big they are, and what kind of access they allow. Once that's in place, we flip a bit in a control register called CR0, specifically setting bit 0 to 1, and just like that, we are in protected mode. Not really though, because just flipping the bit isn't enough. We also need to reload our segment registers so they point to the right entries in the GDT. And if we skip that, things break fast. But in protected mode, everything gets so much nicer. We don't have that messy memory addressing, just flat linear memory. It's exactly what we want when we're getting ready to load and run a kernel. Right now, it's time to talk about long mode. Long mode is where modern operating systems live, so it gives us access to 64-bit registers, a huge address space that's in theory 16 exabytes, and it gives us support for things like paging, syscall, sysread, and fun stuff that modern operating systems use. However, you can just jump straight into long mode from Rio Mode. You have to go through protected mode first. So that's why we set all that up and had a specific chapter only for protected mode. Because to enable long mode, we need a few more steps that first include having to enable paging using a new structure called Page Map Level 4 or PML4. That is part of the 4-level paging system used in x86-64. And then we set a bit in the EFER, that's a special model specific register that tells the CPU to enable long mode. And then finally we flip the long mode enable flag, jump to 64-bit code, and we are officially in long mode. But just like protected mode, we need a new GDT because our old GDT was designed to 32-bit segments, and now we need to design a GDT that supports 64-bit code segments. Otherwise, the CPU won't know how to handle this new instruction set. And then, once we are in long mode, we can finally say goodbye to segmentation and really start building the kind of kernel that modern systems expect. Alright, so we made it to the end. This is the last phase of the boot process, which is loading the kernel. So at this point, our bootloader has already done a ton of work. So we powered the machine, we ran the post diagnostics, we let BIOS find and load our boot sector, we entered Rio mode, we set up the GDT and switched to protected mode, we set up paging and enabled long mode. And now it's time to actually load the kernel into memory and jump into it. That's all that it is left. And there's a few ways to do this. And in simple bootloaders like the one we'll be designing in the next videos, the kernel is usually just a flat binary file or maybe an ELF executable. More into this later. The bootloader, it needs to locate the kernel on disk, load it into a known memory address, parse the ELF headers if we are using ELF, and jump to the kernel's entry point. And jumping into the entry point, the kernel takes full control, so it will initialize the system further, setting up drivers, memory management, and eventually launches user space. And from here on, the bootloader steps aside and OS takes the stage. So I made this diagram to make sure we understand every part of the boot process, from the post diagnostics to the kernel being loaded into memory. And take your time. I think that I made a very good job in this diagram. There's a lot of I skipped. I didn't talk about the CR0 register, but in a general way, I think it works fine. But in the next videos, however, we're gonna be starting designing our bootloader. So we're gonna go back all the way into Rio Mode and start thinking about what we need to do to build our bootloader. So this video was 100% theoretical, was explaining, there was no programming on it. So I will follow this model for theoretical videos. However, for programming videos, I will follow my old model, which is just my camera and my computer screen. And yeah, I think that's all. Thanks for watching, and I'll see you next time.